copy of the video, just put it in the chat before you leave that you want me to send it to you. But I don't think I'm going to post it on YouTube. I haven't really decided that yet, but the whole benefit was for people to show up so they could actually get, real-time questions answered. So I don't know if it's exactly beneficial to just post it on YouTube because I don't know. We'll see. I'll decide later. But yeah, I guess we're just gonna jump into it. The way it's gonna end up working is we're going to kind of go through the first few lessons and then we'll take a break and then jump into equilibrium. And then at the end, I have like a couple basic tips and then yeah, and then questions until 2:00. I'd kind of like to be out by 2, but if it stays till 2:30, that's fine. Any questions before we start? Oh, also, if you guys have questions, I can't see the chat because I can't keep it open while I go through it. So just unmute yourself and interrupt me. That's totally fine. So any questions before we start? Cool. Silence is a no. All right. So for anyone who hasn't gotten the announcement yet, there's going to be 3 questions on the exam. The first 2 are going to be 2-dimensional equilibrium, and the third one is going to be 3-dimensional equilibrium. So basically, in terms of understanding the problem solving, you only have to understand how to approach the equilibrium problems, but know that they're going to try to work as many of the other topics into those problems already. And you can kind of see that in the review problems on, I believe it's the lesson 12 review, because those are old exams. So everyone's going to come in on Wednesday. So we're only doing the exam on one day. So it's not like 2 different exam seatings. So everyone's going to come in at 7:30 on Wednesday. And cohort A is going to be in room 433. And I will be proctoring that one. Cohort B is going to be in the normal room, so 2:30. And Dr. Hari Haran is going to be proctoring that one. The only thing you guys need to bring is like a pencil, a calculator, a straight edge if you really want it, and then just make sure that you've gotten enough sleep and you've eaten something because it is kind of a pretty long exam to be doing like problem solving for that consecutive amount of time. Important, they will yell at you for using pen, so definitely make sure you have a pencil. I'll bring a couple extra ones, but no promises that Dr. Hari Haran will, so just do your best to bring one. If you need me to bring one for you, just let me know. What we're going to provide is we're obviously going to give you the problems. It's going to be formatted almost exactly like a worksheet, just stapled together. We're going to have as much extra printer paper as your heart desires. So if you're annoying like me and you want the entire front of the page that you're given to be your free body diagram so that you can draw it huge and not confusing, do that because we have unlimited printer paper to give you after that. We're going to give you all of the reference card stuff like we did for the quiz. The important thing, I don't remember if Dr. Hari Haran was told this or not, but just make sure that before you start the quiz, the exam, there's no writing on the reference cards. Because if we're walking around and we see that, we have to like yell at you. I don't know exactly what we do, but it's not good. So just make sure that there's no writing on them. Any questions about that before I keep going? Cool. So lesson 1, just jumping right in, was unit conversions and trig. You're definitely not going to have to do unit conversions for like feet to meters kind of thing. Like they're going to give you the problem in the units they want. The important thing to remember for this is that gravity has 2 different values. So if you're in the metric system, it's 9.81. But if you're in the American units, it's 32.2. So that's the important thing to remember for this one. But actually, now that I think about it, I don't think we use gravity in this exam. So ignore that. In terms of trig, this is something to absolutely practice because every single problem is going to have some sort of trig in it, and it's not going to be 45 degrees. So practice between your like 30, 60, 90 triangles and like figuring out what components of the force are 30 and what are 60. and then practice practice slope triangles. And then the important thing that I wanted to point out is that a lot of the mistakes that people make are just assuming that because it's the X direction you use cosine and because it's the Y direction you use sine. That's not the case. So make sure that you're looking at it in terms of which side is adjacent to the angle that's labeled. And the way that I usually think about that is, so when you're given an angle, it's labeled with that little arc thing, and it says like that arc and then 30 degrees, for example. That arc will always go through the hypotenuse and one other side of the triangle. So the side that it goes through that isn't the hypotenuse always gets cosine, and the other side always gets sine. So it's not necessarily like X is cosine, Y is sine, but it's based on how the angle is labeled. Questions on that? No. All right, lesson 2 goes into two-dimensional forces and their resultants. So basically, if you're given a diagonal force, you should be able to break it into their X and Y components, or the components that are parallel and perpendicular to the slope, whichever one's easier for the problem. This is entirely trig, so it's exactly the same thing as lesson 1, kind of, because you have to use the trig to find the components. We'll kind of go into that a little bit more moving forward, but you pretty much use that in almost every single like you use that in one of the steps of every single other lesson. So that's definitely something that you want to make sure you're 100% comfortable with. I don't necessarily think you have to know like by definition what concurrent versus non-concurrent means, but it helps you understand why problem solving is the way it is for some of these things. So like, for example, two-dimensional particle equilibrium, right? Particle equilibrium is always going to be a concurrent system because everything is acting on the particle, which is assumed to be an infinitely small point, right? So for that reason, you can't take a moment. But anytime something is non-concurrent, some net force will cause some net rotation because not everything is acting on one point. So in a non-concurrent system, or in the case of rigid body equilibrium, you're going to end up having some moment that you have to consider. And then the resultant force basically is, once you resolve the forces into their components, you add all of the X components together and all of the Y components together, and then solve for the magnitude using those two. So the important thing is the resultant force as a value is supposed to identify how much of all of those forces is actually acting on the body itself, which means you're essentially eliminating the components of those forces that are playing tug of war with each other. So for that reason, you have to assume that one direction is positive, one direction is negative. It doesn't necessarily matter which one you choose, but I personally always choose right as positive and left as negative, just because that's more logical to me. But again, it doesn't matter. All you know is that if you get a negative answer, you assumed that the direction that you called positive, that assumption was wrong. Which doesn't matter. You can just flip the sign and flip the direction. But you have to call one side positive, one side negative. Any questions on this? Like, it sounds kind of like silly because you guys have been doing it all semester pretty much at this point, but this is the stuff that people usually mess up. It's usually not the actual equilibrium part. It's the little things at the beginning. So if you have any questions at all, now is the time to ask it. Okie doke. All right, so lesson 3 is kind of going into the 3D forces and how to find the force vector, right? So a unit vector, again, conceptually is just a vector in a certain direction with a magnitude of 1. And basically the reason you want that is because it's essentially your slope triangle in a vector form. So it tells you the direction that it's going in, and then you can multiply the magnitude into that vector without changing the strength of the force. And the example that I used in my video, my like review video, was I know that generally I'm pushing my pencil across the counter in the direction of Publix, right? Obviously, it's not going all the way to Publix, but I know it's in that direction. So if I can find a vector that describes that direction, then I can, sorry, someone's in the waiting room. If I find a vector that can describe that direction, I can find the magnitude of it and cancel that magnitude out so that I just have the direction, and then I can multiply how hard I'm actually pushing that pencil into that vector. So now I know exactly how hard I'm pushing in each direction to get my pencil 3 feet away from me, but in the direction of Publix. So that's conceptually what happens. Mathematically, the steps are essentially you have to find a vector describing the direction that the force is going in. So usually you'll be given 2 points that the force is like going from and then going to, and then you do head minus tail, so where it's going to minus where it's coming from, and then that's the position vector. So that's essentially from here to Publix. And then you find out how, like, the magnitude of that vector, right? So that's going to have an inherent distance built into it. So once you find that, you have to divide the position vector you found by its own magnitude to get a vector that has the same ratio of components, but with a magnitude of 1. And then once you have that, you can multiply the magnitude of the force, which is usually given in the problem, into that unit vector, and then you'll have a vector with the appropriate magnitude and the appropriate like ratio of directions. Does that make sense? Because this concept here, the 3D forces, like finding the force vector, comes up a few times later on. And this piece, this position vector describing the direction that the force is going, that is commonly used as the position vector for the moments, like the 3D moments, and that's wrong. So this is important that you know this, and then later on when we get to 3D moments, the position vector that you cross with F is different. So do these steps make sense? Cool. So one thing I forgot to say before I started is that I pretty much have set up a step-by-step way for you guys to go through these problems for all of the like major lessons. So all of the background information is in black text. All of like the actual steps I recommend going through are in purple. So if you are like screenshotting or writing anything down, it should be the purple stuff, because that's the stuff that's actually going to help you with the problem. So if anyone's taking pictures or screenshotting or anything, I'll give you a second to do that. But yeah, now that's what you should be screenshotting, is the purple. Okay. Any questions on lesson 3? I'm either explaining it very well or no one wants to ask questions. Cool. I'm going to take that as a compliment. So lesson 4 is 2D moments. So basically a moment is describing how a force causes like the body you're looking at to want to rotate or pivot, right? So that's what a moment is. And then in terms of 2-dimensional moments, it's a lot easier to do it in like scalar math versus vector math. So I know when O'Neill went over it in his video, he went over it using vectors, and that's fine because it's technically correct. But I think in terms of the time that you're going to spend on these problems, if you do it that way, it's smarter to do it in scalar. So basically the scalar version of this is that the moment that a force causes about a certain point is the magnitude of the force times the distance that the force is away from the point you're looking at. So if I'm taking the moment about A, if I'm looking at the moment caused by force 1 about point A, my D perpendicular is going to be how far force 1 is from point A. And then the magnitude of F is just going to be the magnitude of force 1. So one thing to remember is that especially on like a beam kind of structure, a force is going to have, like there might be a force component that goes through the point. And any force component that goes through point A in that situation is going to have a D perpendicular of 0 because it physically crosses through the point. And then therefore that component isn't going to cause a moment. So just like, I don't know if I've mentioned this yet, but anytime you're looking at a 2D moments problem, my suggestion would be to immediately convert any kind of diagonal force into its components. And then a good rule of thumb, I put it in the red font on the bottom right corner, but a good rule of thumb is if you are trying to use a D perpendicular and you're not given that dimension on the problem, like in the problem, you're doing something wrong. So either you're not supposed to be considering that force, or your components are off, or something like that. So there were a couple people on the exam. So for couples, we'll get into this in a second, but for couples, you don't consider it if the components are pointing at each other. So if you are looking at, it's fairly similar. So the D perpendicular would be if the force is going through point A. So just kind of figure out exactly where the line of action would be going, and that line of action will usually have a labeled dimension connecting it to A if it's necessary to consider that. People are joining like crazy. Okay, so in terms of like the steps to actually solve it, the first thing, again, as I said, would be to break all the forces into their components. And then first of all, you want to pick a moment that you want to take, or pick a point where you want to take the moment about. So in terms of 2D equilibrium problems, because that's what you're going to see on the exam, that'll be the point that has the most unknowns, which usually is a point where there's a support that you've taken off your free body, or that you've removed the body from. And then, yes. So by choosing that point, you are able to cancel all of those unknowns and solve for other ones that are not going through that point. And I'll show you that in a second if we look at like a practice problem. I'd also like to apologize for all of the background noise because my family decided that right now is the time to be the loudest they've been all day. So once you found your force components and you've found the point that you want to take the moment about, identify which components go through the point you're looking at and cross them out. So that'll usually be the components that don't have some dimension connecting the side of the arrow to point that you're looking at. So if it's pointing directly towards or away from the point you're looking at, it has a D perpendicular of 0. But also verify that there's a dimension for all of the forces that you're looking at, if that makes sense. And again, I'll show you that on a problem so it's more concrete, but they're not going to ask you to just suddenly make up dimensions. So in terms of your next step, you have to decide whether you're calling clockwise or counterclockwise positive, because just like for the resultant force, there's going to be some sense of tug of war in terms of how these forces want to cause that body to rotate. So I usually call clockwise positive, but it doesn't matter again because if you assume the wrong direction, you'll just get a negative answer and you can flip the sign, flip the direction, and you're fine. So it's whatever your personal preference is. I usually just go with clockwise. So your last step is to set up an equation that considers the moment that all the forces that you didn't eliminate cause. So essentially, what you're going to end up looking for is the magnitude of the component that you're looking at. So if it's a force that was originally vertical, it's just the whole thing. If it's a force that is originally at some sort of diagonal and you only want the vertical piece of that, then it's the magnitude of that component. So just make sure you're considering only the portion of the force that you're looking at. And then you want to find the perpendicular distance between the force component that you're looking at and the point that you're taking the moment about. And again, that's going to be measured from essentially the side of the arrow to the point you care about, and not almost 100% of the time, unless it's like an unknown, it's going to be given to you. So if it's not blatantly obvious what the perpendicular distance is, you've probably either drawn your components in the wrong spot or it's not supposed to be considered. So double check that. And then the last thing is to double check your positive and negatives based on how that one force component you're looking at causes the body to rotate. So again, if I'm pinning it at A, if I'm taking the moment at A, physically put your finger on the exam paper on point A and pull down or push up on the force and see how it causes your exam paper to rotate. And I was literally the person that did that in class on the exam, and I got it right every time. So absolutely recommend that. Any questions about this before I move on?
No, no questions on it.
Yeah, what's up?
No, I don't have a question.
Oh, okay.
Thanks.
Anyone else? Okay. Okay, I guess moving forward then. All right, so lesson 5 is 3D moments, and it's exactly the same conceptual stuff as 2D, but now your math looks a little different. So this is kind of what I was talking about when we were going over lesson 3 stuff. This R is different than the R that's a part of this calculation. So there's an R that is a part of the lesson 3. Hold on, my dogs are doing the thing. The Amazon guy's here. Okay, I think they're good. But there's an R or a position vector that's embedded into the calculation to find the force vector, and that's different than the R that you're crossing it with. So the R that you're crossing it with is a position vector connecting the force to the point you're looking at. So if I'm finding the moment about A caused by force 1, for example, I'm looking for, in this R right here, the R that I'm crossing with F, I'm looking for a force that's gonna, or a vector that's gonna connect the force to the point. When I'm looking at finding this F, I'm looking at a position vector in the direction of the force. So there's 2 different position vectors, and that's almost where everyone's mistakes on these kinds of calculations come from, is confusing the R's. So if you have any kind of like question or confusion with stuff like that, now is the time to ask, because I mean, I have answers. So questions on this before I go into the actual steps? Okay. Well, here's the steps. Same equation. So step one is to find the position vector that you're using in the cross product. So the position vector that connects the force to the point you care about. And then similar to two-dimensional moments, you're taking the moment about the force with the most, or about the point with the most unknowns. And especially in 3D, it's usually the point that the fixture was at, or the support was at. So once you find R, you want to find F. And we find F by doing the same steps that you used in lesson 3, where you find a position vector that is in the direction of the force you're looking at. You find the magnitude of that position vector, divide it by its magnitude, and then multiply the magnitude of the force that's given to you on the exam. So that's that. Then you want to use your cross product and your calculator to do R cross F. If you haven't programmed your calculator yet, first of all, why? But second of all, stay after this review thing so I can help you program it, because it eliminates the possibility of math mistakes and it gives you more time on the exam. That's not to say that you have to program your calculator. You can absolutely do it by hand if you're comfortable doing it like that. I just don't know why you wouldn't want to save time. But that's up to you. And then at the end, if you want to find the resultant, oh, that's supposed to say resultant moment, not couple. You essentially stack them, right? So write all of the moments that each force that you're looking at causes, and then add all the x's together, add all the y's together, and add all the z's together. And basically what you're going to get is a vector that's obviously the x component, y component, z component, and then you're going to have either foot-pounds or Newton meters, and then about some point. So you don't have to say clockwise or counterclockwise because the direction is already embedded into here. And in 3D, it's really kind of hard to identify one like clockwise versus another, because usually it's clockwise is a two-dimensional thing. So that's that. Any questions about these steps? This is super important. Okay. All right, lesson 6 was couples. Very, very similar to moments. It's just the D perpendicular, or this R, is different. So D perpendicular is the perpendicular distance between the two forces that make up the couple, right? So in this case, especially if you have diagonal couple forces, right? Or like forces that are making up a couple, you want to break them into their components, because their components are going to be couples too. And it'll be much clearer which pieces you actually need to use in order to find the overall couple. So that was kind of confusing the way I just worded that. So basically, if they're diagonal, you have to break it into the vertical and horizontal components so that A, it's easier for you to identify which distance is labeled, right? Because then you're going to have a much easier time finding the labeled dimension on the drawing that was given that corresponds to D perpendicular. But also it'll be much, much clearer to figure out whether you need to consider both of those pieces, right? Both of those components, or just one. So on the quiz, there was one couple for both cohorts. There was one couple that was diagonal and one that was completely vertical. The one that was completely vertical was very straightforward and no one got it wrong. I don't think literally anyone got it wrong. It was just like the magnitude of the force times obviously the completely horizontal perpendicular distance between them. But the diagonal forces, the horizontal components had a labeled distance between them, but the vertical components passed through each other. So because they passed through each other, the perpendicular distance is 0. More conceptually, that kind of makes sense, because if you put your pen down on the table in front of you and try to push exactly on either side of the pencil right towards you, like your other finger, it's not going to want to rotate because you're just pushing at the same point. And then I guess another way to think about it is they share a line of action. So, but that's just justification that D perpendicular is 0. So any questions about that before I go into the actual order that I recommend doing the steps? Okay. All right, so the order of how I recommend doing it is first, before you do anything else, break up the diagonal forces into their components, because the components will be couples too, so that's totally valid. And then, like I said, find which components you don't need to consider. So if they pass through each other, you don't need to consider them. So on the quiz, I mean, like, to kind of put it more solidly in your head, I'm talking about like the vertical component of the diagonal. Oh, sorry. The vertical component of the diagonal, because those cancel each other out. And then if you don't need to use them in your equation, cross them out, erase them, something that will indicate to you that you don't need to do it. And then find the perpendicular distance for each component that you're looking at. Again, just like moments, it's going to be something that's labeled and very clear to use it. So if you're having trouble finding D perpendicular, it means that you probably are considering something that you shouldn't be. But again, remember that in this situation, unlike moments, you're looking for the distance between the arrows, not the distance between one arrow and some other point. It's the distance between the arrows. And then on the quiz, it said to find the resultant couple. So you find that by establishing, again, one direction that you're going to call positive. Again, I always call clockwise positive. And then you think about which way the couple causes your paper to spin if you push it in those directions. So if you have your left arrow is pointing up and your right arrow is pointing down, that's going to cause the page to spin clockwise. So that would be positive in my equation. That force times distance would be positive in my equation. Similarly, if I have my left arrow is pointing down, my right arrow is pointing up, that's going to go counterclockwise, so it's negative in my equation. And then you just add those up based on the positives and negatives that you just found, and you're going to get some number. And then your units are going to be foot-pounds or Newton meters. And then your direction for 2D is going to be either clockwise or counterclockwise. Or if you end up doing 3D, which I just realized I didn't type up directions for, it's going to be the exact same as these steps, except your position vector is going to be from one point on the line of action of one of the forces to another point on the line of action of the other force. So it'll be the same steps. And then to find the resultant, you just add each component downwards. Any questions on couples?
So like a problem like that wouldn't be on the test, right? Like we wouldn't have to do that.
I don't think so, but when you're going through the worksheets in lesson 12, if you see a couple in the problem, see how they look, how they solve for it. But I don't know exactly, I don't think they would be able to put that in a problem itself, like an equilibrium problem. Good question. Anyone else? Okay. On to lesson 7 and 8. Oh, wait, actually, you know what? Let's take like a 5-minute break because we've been going for about 30 minutes now. So let's take like a 5-minute break, and then we'll get into equilibrium. So I guess come back at 12:50. Okay, so it's been 5 minutes, so I guess we'll start again. Let's see. So jumping right into equilibrium, um, the whole premise is that first of all we're in statics, and so because of that things aren't moving. But equilibrium in statics means that because things aren't moving, that must mean that there's no overall force acting on the body. So essentially the resultant force and the resultant moment is zero. So in other words, all of the forces that are acting on the body should balance and should essentially completely end up being contributed to some sort of tug of war situation. So in terms of steps, again, start by breaking their forces into the components. And then the new part about equilibrium problems is that there's going to be some set of unknowns and some set of knowns. So figure out what the question is asking for and make sure that you have less than 3 unknowns, because you're only going to have 3 equations. And those equations are that the sum of the forces in the x direction, some of the forces in the y direction, and then some of the moments about some point equals 0. So in that case, you can then solve for your unknowns using those 3 equations. And then it's the exact same process. So for the x and y equations, it's the exact same processes as finding the resultant force, right? So you look at all your components, you add up each component, and then figure out exactly how those pieces are contributing to the, I guess, force balance of the system. And then your unknown will be in that equation too. And then you can figure out how to find the unknown from there. And then for the moment equation, again, it's the same thing as finding a resultant moment in 2 dimensions. You just do force times perpendicular distance for everything that matters. And then from there, what you can do is just go in and figure out what your moment equation can do in terms of helping you find the rest of your unknowns. So generally what happens is in 2D equilibrium problems, first of all, your unknowns are usually reactions or tensions, right? So what's going to happen is, for example, if you have a beam that has a pin on one side and a roller on the other side, you'll have 2 forces at the pin, 2 reaction forces at the pin, and 1 reaction force at the roller. So essentially what's going to happen is you'll have 1 unknown in your x direction and 2 unknowns in your y direction. So your moment equation comes in by allowing you to take the moment about one of those points, either the point where the pin's at or the point where the roller's at, to find how to essentially cancel out one of your vertical unknowns and solve for the other one. And you can then plug it back into the y direction equation. But the important thing to know in terms of like logicking through these problems is the pin like reactions, or like the support reactions, I'm sorry. So because most of your unknowns are going to come from reactions, you have to be comfortable with finding out how to identify those reactions. And I said this in, I think it must have been my 2D equilibrium video, but basically the reactions come from any direction that the body can't move because of its supports. And then you won't have reaction forces in any direction that the body can move. So for example, a pin has a vertical and horizontal force reaction, but it doesn't have a moment reaction because a pin is essentially just a hinge. So I can't pull the body one way or the other, but I can absolutely rotate it about the pin. So because I can rotate it about the pin, there's nothing in the pin that's preventing me from moving it, if that makes sense. So that same logic, it could be a support you've never seen before. But if you follow that logic can I move it in the X direction? Can I move it in the Y direction? And can I rotate it? If you follow that logic, every single time you replace a support with a force, you'll get it right every time. But don't just skip through it and assume you know it, and please don't try to memorize it. Because yes, there's a table in your textbook that has a bunch of them, but you'll forget it 100%. So my recommendation would be, if you want to use the table, use it to try to walk yourself or practice identifying where your unknowns should be and justify why they're there in the textbook. And then once you find your unknowns and draw your free body diagram, from there, it's just a matter of using lessons 1 through 6 to solve your problems. Questions? Y'all have to have some questions. Okay. All right. So lessons 9 and 10 are a little bit more complicated just because of like the problem solving like structure that we kind of ask for. So still things don't move, which means there's no overall force, which means essentially you want to find out where your unknowns fit into the equation, set the equations equal to 0, and then solve. In 3 dimensions, you're going to have up to 6 equations and up to 6 unknowns, right? So basically what's going to happen is the 3 unknowns you could have, or I mean the 3, how do I say this? I'm not going to say that because that's confusing. But anyway, so you have this table in your reference card. So the important thing is not to remember the table, but it's to remember exactly how to use the table and how to find each component of the table. So the leftmost column, forces, moments, and reactions, is literally just a list so that you can remember exactly what things you need to consider in the rest of the problem solving. So that's literally just a place for you to remind yourself exactly what you need to consider. The second column is a position vector connecting the force to the point you're taking the moment about. So if you're taking a moment about the support, like the support reaction, then you have to end up using this column to connect each of the forces you're looking at to that point. Give me 1 second because my dogs are about to freak out. Hold on.
I have a question.
Yeah, what's up?
So I wanted to know, because there's only 3 questions on the exam, like how the points work. Like, is the professor like looking for us to like have like our like diagram on there and like all the numbers like clearly written out? Like, what does he like look for to give us points?
I will get to that right after I go through lessons 9 and 10.
Okay.
I promise.
Mhm.
That's a good question though. So I guess continuing with this, the second column is, like I said, a position vector that indicates some connection between a point on the line of action of the force to the point that you're caring about. So it has nothing to do with the direction of the force itself. The third column is exactly the same steps as lesson 3. I don't know if you figured it out by now, but lesson 3 is probably one of the things you want to be the most comfortable with. That and trig, but this column is essentially do lesson 3. So it's you find the position vector describing the direction of the force, you find its magnitude, divide the position vector or the position vector by its magnitude to get the unit vector, and then multiply the given force into it. If you have unknown forces at a pin reaction or at a support reaction, you put those here. if you have unknown moments at a support, then you put those here. So you end up, if you are looking for unknown moments, you end up not using these columns because a moment is already R cross F. So you don't do it again. So if you have unknown moments, you just skip right over to the third column and put MY, MX, MZ. And then if you have unknown forces, you end up putting AX, AY, AZ, or whatever the point is, X, Y, Z. And then once you fill this out, you sum all the way down each of the directions for this column, and that gets you your force equation. So essentially some of the F or some of the forces in the X direction is 0, some of the forces in the Y direction is 0, some of the forces in the Z direction is 0. And then you sum down each of these columns and you get the moments in each direction equals 0. And then you have your 6 equations. Any questions about this before we move forward? Because this is the
Will you
last.
be doing any examples of these, or should I just look at the ones on Canvas?
I can in the extra time at the end if you want me to. But I would hesitate. I'm not going to do very many because I don't want to walk you through the problems that you have at your use. You know what I mean? Because there's only a handful of problems.
Yeah. Because like I have trouble like picking out what specifically I need to put in this table, like all the little details. So I was just wondering.
Okay, yeah, we can absolutely do one of these because it kind of encompasses everything. So yeah, we can absolutely do one of these.
Okay, I'd appreciate it because like I kind of get the processes mixed up. So thank
Okay.
you.
Yeah, for sure. Anyone else have questions about content before we go on to like what the exam is going to look like in terms of grading and then what you should do for like partial credit and stuff? Okay. So fun fact about Allie, oh, I guess I don't have this slide in here anymore. But fun fact about Allie is I think I only got 2 exam questions completely correct in this class, like total, ever. And I ended with an A in the class. So you absolutely don't need to get an answer completely correct to get it, or to get an A in the class. So first of all, I wanted to put that out there because y'all are going to leave the room and talk to each other about exactly what answers you got, and then you're all going to panic because you're all going to have different answers. So don't do that because I was the person that never had the same answer as anyone else because mine were always wrong. And I still got an A. So it has no indication of how you're going to do on the exam. Just want to put that out there first. Secondly, in terms of the actual grading, okay, so there's 3 questions. It'll be out of 300 points. So essentially each question is going to be 100 points. I would say 15 to 25% of the points on each question are going to be on your free body diagrams. So just remember that your free body diagrams are just the structure itself. So don't put any of the supports, don't put anything around it. So it's just the structure itself. All of the forces acting on it, all of the moments acting on it, that kind of stuff, your dimensions, your units, and then that little like coordinate thing to show which directions you're calling positive. So that's 15 to 25 points for each question. So that's already almost what? 25% of the credit on the exam. Which also means if you don't draw free body diagrams, the highest grade you can get is a 75. So do with that what you will. But there's that. Then going forward, the way that they grade is with error moving forward or something like that. So basically what ends up happening is if you misread your drawing or like the problem and you put the wrong number on your drawing in your free body diagram, they'll take off like what, 5 points for that, but then they're gonna redo the problem using that number and see if your work was right. So if you make a mistake in one step, obviously the subsequent step using that number are gonna be wrong, but they don't penalize you for every single incorrect step. They penalize you for the one that you goofed up, and then assume you're doing everything right going forward and double check that. So if you do what I usually do, where you can't figure out how to use your calculator right, and you add two numbers instead of subtracting two numbers, you'll get points off from that. But every step moving forward that uses that problem or that number is not going to be marked wrong if you do those right. So that's kind of that, which is also why they really hate when you ask them how long it's going to be before you get your grades back, because they literally end up doing 3 problems for 40 students almost every single time, because almost no one will get the same answer. So do yourself a favor and don't ask them when your exam grades are going to be back. Usually it's a week and a half. Basically what ends up happening in terms of timing, I would suggest that the 3D problem takes up a little bit more time, but because it's a longer amount of steps or more steps, it's going to be a simpler problem, if that makes sense. So I would almost count on your 2D problems being a little bit more complicated and your 3D problem being less complicated, only because there's, I don't want to say more steps, but it's like more complicated. Any other questions about how like grading works or how the actual exam works?
So basically, it's only 3 questions, and it's going to be 2D equilibrium and 3D equilibrium, and that's it?
Yes. And the way that works is that they end up incorporating lessons 1 through 6 into those types of problems so that they can still test you on 1 through 6, but in a more reasonable way.
Okay, thank you.
Mm-hmm. Any other questions? Okay. In terms of like how to best prepare for the exams, my recommendation would be to start looking at some of the homework questions. And if you realize that there's like a type of problem where, or like a type of like subject, like if you really don't understand moments, go back to the moments like lesson. First of all, watch my video and see if that clarifies it for you, because I explain it in a slightly more student friendly way than the professors do. So watch the video, see if that clarifies it. If that doesn't, go to the lesson module and try to look at the solutions for the lesson worksheets and see if that kind of clarifies it a little bit. See if you can find the pattern there. And then if not, come to office hours and I'll figure out a different way to explain it to you. But my recommendation would be is to use the homework problems to identify what you're struggling with, practice those, and then go into the exam review module. I think it's lesson 12, I think. So yeah, go into the lesson 12 stuff and say, all right, essentially it's structured so that problems 1 through 3 were one exam, and then 4 through 6 were another exam, and 7 through 9 were a third exam. So essentially you have 3 past exams available to you. So my recommendation would be is to treat those like an exam. So print them out, staple them together, and sit down and try to take them or answer those questions in a like 100 and how long is your class? It's 7:30 to 9:10. So however long that is, try to answer it in that time frame. But again, my suggestion would be to not start off with the exam review questions, if that makes sense. And then I can't stress this enough. this class grade and this exam grade just the same is absolutely a matter of how much work you put in before the exam. Because these problems aren't something that you can like memorize, it's something that you get familiar going through the process. So you have to familiarize yourself with the process, or else you're going to go in and say, all right, I know everything conceptually, but I have absolutely no idea how to make it happen. So it sucks that really the only way to do well is to sit there and do as many practice problems as you can possibly do before Wednesday, but that's pretty much the way to get an A. So any questions on that before I open it up to the rest of the concept questions you guys might have? All right, silence is a no. So I guess that's the rest, or that's all I really wanted to go over in the review.